So very good afternoon to everyone. My name is Christopher Tang Zizhen, and my student ID is EGE 2409037. So today I would like to talk about my topic, which is called the application of linear system in science and engineering. So be more specific, it's going to be the electrical circuit analysis. So at first, I would like to introduce about my topic. And at the middle, I will give an example, which is the calculations. And lastly, I will give the applications of my topic. Okay. So at first, I would like to introduce my linear system, which is what is very important in linear system. So the relationship between the variable like the voltage V, current I, and resistance R is going to generate a formula which is called the V equals to IR. So there are three types of linear system in different kind of solution. So if it's in one solution, it's going to be the consistent and independence. If it's going to have a lot of different kind of infinite many solutions, it's going to be the consistent and independent. So if it's like zero solution, which is no solution, it's going to be inconsistent, which I think we mentioned in our class for the chapter one before. And lastly, it's going to be the Kirchhoff voltage law (KVL) and the Kirchhoff current law (KCL). So linear system in circuit and analysis. So the first is going to be it can model the circuit and predict the change when the resistor or the voltage source vary. And the second is going to be it can calculate the unknown variables such as the current in each part of circuit, which is using the formula like V equals to IR or other formula to calculate the value. And lastly, it is ensured that the electrical system are optimized for energy efficiency while meeting the safety standards. Okay, circuit fundamental. So as you can see, I have mentioned about four circuit fundamental, which is the first is going to be the series, parallel, KCL, and KVL. Yeah. So the first series, so the first is going to be the series, which is arranged in the single path when the current remain constant throughout, which is mean that like you're going to have only one wire to connect all the stuff. Yeah, the light bulb, the battery, all the stuff. So the second is going to be the parallel, which is arranged in the separate path, allow them to share the same voltage across each bond, which means that as you can see as I write inside, separate arranged in separate paths, which is mean that it's gonna have a lot of wire connect to each other for only so that they can share the same voltage. Yeah. The third is gonna be the KCL, which is means that the total current entering a junction in the system is equal to the total current leaving the junction, which is mean that how much current that will enter into junction, and so it's equal to how much the current will be leaving. So for example, like I have 10 current going inside, so when you're leaving, the 10 current also will be go away. So as you can see, I write the formula, the I1 plus I2 equals to I3. Yeah. The lastly is going to be the KVL, which is means that the total voltage around any closed loop in the circuit is zero, which is means that VAB plus VBC plus VCD plus VDA is equal to zero. Yeah. So it means like when you go one circle and the end is going to be zero. So now I'd like to talk about the mathematic framework, which is like applying the Kirchhoff's law to the DC circuit. It is a step-by-step strategy for solving the circuit problem. Yeah. Yeah. So just like just now I mentioned about the KC and KVL. So I would like to talk it about again, so to let you guys to be more understand about it. So the first KCL current flow, the total current flowing into the nut is equal to the total current flowing out. Yeah, so I think it is very easy to understand as I already write the symbol I in enter is equal to I out. Yeah. So for the second Kirchhoff voltage law, the KVL, which is the total drop around a closed loop is equal to the total voltage gain. So as you can see, you can see I also have write the formula down. As you can see, the first symbol, which is means that the total, which is the sum voltage drop inside the closed loop is equal to the sum of the voltage rising up. So now I'd like to give a calculation. As you can see, this is the example of the circuit. So as you can see inside the circuit, we have the R1, R2, and R3, which is have different ohms, which is the 10 ohms, 20 ohms, and the 40 ohms. And I also have mentioned about the voltage source, which as you can see in the picture, V1 equals to 10 volts, V2 equals to 20 volts, and also the unknown current I1, I2, and I3. So as you can see at this slide, so we need to find the unknown current, which is the I1, I2, and I3. So before finding the current, so we're going to apply the Kirchhoff current law, which is the KCL and the KVL for this example of circuit. Yeah, so for the KCL, so as you can see, the node A, I1 plus I2 equals to I3. Node B, I3 is equal to the I1 plus I2. For another Kirchhoff voltage law, KVL, it's going to be, so as you can see at the loop 1, 10 is equal to the I1 plus 40 I3. Yeah, first. The log 2 is going to be 20 is equal to 20 I2 plus 40 I3. Yeah. So for the lastly, which is the log 3, is 10 minus 20 is equal to 10 I1 minus 20 I2. So after we have the law, which is the KCL and the KVL for the formula. So now so now we're going to substitution the I3 equals to I1 plus I2. So from the log 1, as you can see, 10 I1 plus 40 I2 is bracket the I1 plus I2 equal to 10. 10 I1 plus 40 I1 plus 40 I2 equal to 10. So after calculation, it's going to be 50 I1 plus 50 I2 equals to 10. So from the log 2, I think I no need to annoy grandma nagging a lot. So as you can see, it's a 40 I1 plus 60 I2 equals to 20. Yeah. So wait a minute. Yeah. So after that, as you can see, we have this two simultaneous equation, which is the 50 I1 plus 40 I2 equals to 10, 40 I2 plus 60 I2 equals to 20. Yeah, so as you can see, it's only have two equations. So if you had done mathematics before, it's just a substitution method. So it's going to be very easy. Yeah, as you can see, I have wrote down here, which means that form equation 1, which is the first equations. So after you form already, so it's going to be I1 equals to 0.2 minus 0.8 I2. Okay, so if the word is too small or too ugly, I'm sorry for that. Yeah. So after when you have I1s, so we're going to sub the I1s into the second equation, which is the 40 I1 plus 60 I2 equals to 20. So after you sub inside, it's going to be 40 I2 plus 60 I2 equals to 20, 40 bracket, which is sub the I1 value into the 40 I1 in equation 2. So it's going to be 8 minus 32 I2 plus 60 I2 equal to 20, 28 I2 equal to I2. I2 equal to 0.4298 current. So after when you have I2 already, so we're going to sub the I2 value into the first equation, which is the 50 I1 plus 40 I2 equals to 10. The reason that we sub the I2 into the first equation is because that at first we have found the I1 value, but it is 0.2 minus 0.8 I2. So we are sub inside. So after when you sub inside the I2 into the I1 equals to 0.2 minus 0.8 I2, so we're going to get a final answer, which is the I1 equals to negative 0.143 ampere. Yeah, so and now we're gonna apply the formula, which is the I3 equals to I2 plus I1. So the reason that we want to find the I3 is because at the previous slide I have talked about, because we don't know the unknown current. So after we calculation, we found out that the I1 value and I2 value, and now we're gonna find the I3 value. So how to find the I3 value, since we don't have the equation? So as I have right inside here, we're gonna use the Kirchhoff current law, which is the KCL, which is the I3 equals to I1 plus I2. Yeah, so let me go to the last slide, which is the I2, which is the I1 plus I2 equals to I3. Yeah, as you can see at the last here. I'm not sure why I didn't do it, but I'm gonna do it now, so we're gonna be very fast. Yeah. Okay, welcome back. So after having the calculation, the answer is gonna be 0.286 at current. Yeah. So I will write the final answer at here later. Okay. And now I'm going to be the left hand side, which is the result interpretation. So the negative I1 indicate the current flow into the opposite directions to assume 1. Voltage across R3 is equal to 0.286 plus 40 is equal to 11.44, which is 11.44 volts. And now it's going to be the last three slide, which is talking about the application of the result. Yeah, so the first is going to be the power optimizations. The application is going to be by analyzing the circuit, engineers aim to optimize the energy usage to cut down the transmission loss and maximize the power output. So for example, in electrical vehicle, circuit analysis optimize the BMS performance by lowering down the power loss, thus enhancing the energy efficiency and range. The second is going to be the circuit design and component selections. The application is going to be precise the analysis to help pick up the suitable components so the circuit work as expected and perform well. So for example, in the smartphone, circuit analysis ensure that the voltage regulator delivers stable power to key component, preventing the overheating and maintaining the performance. Oh, as you can see, you're gonna have E at here. I'm gonna so for all the mistakes I'm gonna redo the correction again and submit the slide to you later. And lastly, it's gonna be the safety system. So for the applications, it's accurate circuit analysis in assigning for designing protective device like fuse and breakers to prevent the failure under the maximum load conditions. So for example, proper analysis of branch currents in the resistance panel is critical for selecting the appropriation rate circuit for the breakers and ensuring the electrical becomes safety. Okay, yeah, so this is the end of my presentations. I hope you like it. And last and final, as I said before, my name is Christopher Tang Zizhen, EG240. Thank you for watching this.